Hello and welcome to this tutorial on finding beam deflection using the double integration method. In this tutorial, we'll be looking at a simply supported beam with 2-point loads, giving us 3 regions to investigate. Let's get to it. In this tutorial, we're given a simply supported beam ABCD of uniform cross-section, carrying 2 equal point loads P placed symmetrically about the midspan. Our aims are to determine the elastic curve, the slope at support A, and the maximum deflection of the beam. This slide is a quick reminder of the standard double integration procedure. We assume that EI is constant within each beam segment. We sketch the elastic curve to identify boundary conditions, write the bending moment in each segment using the method of sections, and we integrate, once to obtain the slope, and second to obtain the deflection expressions. The integration constants are then found from the boundary conditions and continuity of slope and deflection, and the final equations are used to evaluate slope or deflection at any point of interest. First, we sketch the expected elastic curve of the beam. Because the beam is simply supported, the vertical deflection is 0 at supports A and D. The loading is symmetric, so the elastic curve is also symmetric, with a maximum deflection occurring at midspan between the 2 point loads. Next, we determine the bending moment distribution along the beam. Under the 2 equal point loads, the bending moment varies linearly from A to B, constant between B and C, and then varies again from C to D. To analyse this systematically, we'll divide the beam into 3 regions. Region 1 from A to B, Region 2 from B to C, and Region 3 from C to D. In each region, we'll introduce local coordinates. In Region 1, coordinate x1 is measured from support A towards B. In Region 2, coordinate x2 is measured from point B towards C. And in Region 3, coordinate x3 is measured from the right-hand support D back towards C. The distances shown reflect this, with Region 1 and Region 3 each having a length of A and the middle region having a length of L minus 2A. These local coordinates will be used to write the bending moment expressions in each region before we apply the double integration method. We begin by determining the support reactions using equilibrium. First, we consider equilibrium in the horizontal direction. There are no horizontal loads acting on the beam, so the horizontal reaction at A is 0. Next, we take moments about point A. Taking moments about A eliminates the reactions at A and leaves only the reaction at D and the 2 applied loads. Solving the moment equilibrium equation shows that the vertical reaction at D is equal to P. And finally, we apply vertical force equilibrium. The sum of the vertical reactions must balance the 2 applied loads. Since the reaction at D is P, the reaction at A must also be P. So both supports carry equal vertical reactions, which is consistent with the symmetry of the loading and geometry. At the top of this slide, we show the free body diagram of the beam. The 2 point loads act downwards at B and C, and the vertical reactions at A and D are both equal to P. The beam is divided into 3 regions by the location of the point loads, and the distances from each support to the nearest load are A. The distance between the 2 loads is L minus 2A. At the bottom of the slide, we sketch the bending moment diagram and label the bending moment expressions in each region as M1, which is a function of x1, M2, a function of x2, and M3, a function of x3. We'll now write them explicitly using local coordinates defined earlier. At the top of the slide, we remind ourselves of the overall bending moment diagram and the local coordinate systems in each region. Region 1 runs from support A to B and has a length of A. In this region, the local coordinate x1 is measured from A towards B. To determine the bending moment expression in Region 1, we isolate a section at an arbitrary distance x1 from support A. The free body diagram of this cut section is shown at the bottom of the slide. The forces acting on the section are the vertical reaction P at A and the internal shear force and bending moment at the cut. We take moments about the cut section to eliminate the internal shear force, and applying moment equilibrium gives us that M1 minus P times x1 equals 0. Rearranging the bending moment in Region 1 gives us that M1 equals P times x1. This expression is valid for x1 from 0 to A, and will be used next to obtain the slope and deflection in Region 1. In this slide, we identify Region 2, which runs from point B to point C. The local coordinate x2 is measured from B towards C. To find the bending moment expression, we take a cut at an arbitrary distance x2 from point B and isolate the portion of the beam to the left of the cut. Because we start the cut at B, we must include all the internal forces, so the internal shear force and the bending moment at B, together with the external point load P, which is applied at B. This takes into account the contribution of everything to the left of B. If we calculate those internal forces, we'll find that we have a moment of P times A at point B and an internal shear force of P at point B. You can see them marked in dark green. Looking at the section from B to the right and applying moment equilibrium about the cut gives us that M2 minus the moment PA equals 0, because the two P's, the internal shear force and the external P, cancel each other out. This shows that the bending moment in region 2 is independent of x2 and is constant with a value of PA. And this is valid for when x2 is between 0 and L minus 2a. And here on this slide, we identify region 3, which runs from the right-hand support D back towards C. In this region, the local coordinate system x3 is measured from D to C, and that is in the opposite direction to the coordinates we used in regions 1 and 2. To determine the bending moment expression in region 3, we take a cut at an arbitrary distance x3 from support D and isolate the portion of the beam to the right of the cut. At the cut section, we introduce the internal shear force and bending moment, and these internal forces are drawn in the opposite sense to those we used when we cut from the left-hand side. This is essential because internal forces must be equal and opposite on either side of a cut, so they cancel each other out when the full beam is considered. Remember, these are internal forces. The free body diagram therefore shows the internal bending moment M3 acting in the opposite rotational direction, together with the reaction P at support D. Applying moment equilibrium around the cut gives us that minus M3 minus px3 equals 0, and rearranging in region 3 gives us the moment of m3 equals px3. This is valid for x3 between 0 and a. The results mirror the bending moment expression in region 1, but the sign convention and coordinate system are reversed, consistent with the internal forces cancelling across the cut. This slide summarises the bending moment expressions in each region of the beam and the coordinate directions used to obtain them. As we saw, in region 1 from A to B, the bending moment is m1 equals px1, valid for x1 between 0 and a, and the arrow next to the moment indicates that the cut is taken from the left, so x1 increases to the right. In region 2, from B to C, the bending moment is constant and equal to PA, and that is valid for x2 between 0 and L minus 2a. And again, the arrow shows that the cut is taken from the left, with x2 increasing from B towards C. And finally, in region 3, from D to C, the bending moment is px3, and that is valid for x3 between 0 and a. Here, the arrow points to the left, indicating that the cut is taken from the right-hand side of the beam. Coordinate x3 is therefore measured from support D towards C. The arrows are not sign conventions for the moment itself. They simply indicate the direction from which the section is taken and therefore the direction in which the local coordinate increases. We now integrate the bending moment expressions once to obtain the slope or rotation in each region. From beam theory, the governing relationship is that EI theta or EI y tag equals the integration of the moment according to dx. The integration is carried out separately in each region using the local coordinate and bending moment expression appropriate to that region. In region 1, for example, for x1 between 0 and a, the bending moment is px1, and integrating with respect to x1 gives us px1 squared over 2 plus c11. In region 2, the bending moment was a constant pa, and integrating that gives us pax2 plus c21. And in region 3, the bending moment was px3, with x3 measured from the right-hand side support. Integrating with respect to x3 gives us px3 squared over 2 plus c31. The constants of integration are labelled systematically to keep track of both the region and the order of integration. The first index refers to the region number, and the second index indicates that this constant comes from the first integration. For example, C11 is the constant from the first integration in region 1, C21 is the constant from the first integration in region 2, and C31 is the constant from the first integration in region 3. We now integrate the slope expressions to obtain the deflection equations in each region. As before, the integration is carried out separately in each region using the local coordinate for that region. So in region 1, the slope expression was px1 squared over 2 plus c11, and integrating that with respect to x gives us px1 cubed over 6 plus c11 x1 plus c12. In region 2, our slope was pax2 plus c21, and integrating that with respect to x2 gives us pax2 squared over 2 plus C21 times x2 plus C22. And finally, in region 3, the slope was px3 squared over 2 plus C31, and integrating that with respect to x3 gives us px3 cubed over 6 plus C31 times x3 plus C32. The constants introduced at this stage follow the same naming logic as before. The first index identifies the region, and the second indicates that these constants arise from the second integration. For example, C12 is the constant from the second integration in region 1. At this point, we have the expressions for deflection for all three regions, each containing unknown constants that will be determined using boundary conditions at the supports and the continuity of deflection and slope between regions. We'll now move on to evaluating the constants of integration using boundary conditions and continuity. We start by stating the boundary conditions at the supports. Because the beam is simply supported, the vertical deflection at each pinned end must be 0. At the left support A, the coordinate for region 1 is x1 equals 0, so the boundary condition is y1 when x1 equals 0 equals 0. At the right support D, the coordinate for region 3 is x3 equals 0, so we need to take into account the deflection for region 3, and that gives us that y3 when x3 equals 0 equals 0. These two equations are constraints that we will substitute into the deflection expressions later, along with the continuity conditions at B and C to determine the integration constants. We now state the continuity or compatibility conditions at internal points of the beam. At points B and C, both the deflection and the slope must be continuous. This reflects the fact that the beam is physically continuous with no hinges or breaks at these locations. Starting at point B, which connects regions 1 and 2, the slope must be the same on either side of the point. This gives us the condition that the slope y1 when x1 equals a must equal the slope 2 when x2 equals 0. The deflection must also be the same on either side of point B, giving us y1 when x1 equals a has to equal y2 when x2 equals 0. We can now move on to point C, which connects regions 2 and 3. The deflection again matches directly across the point, so we have that y2 when x2 equals L minus 2a has to equal y3 when x3 equals a. For the slope at point C, we need to be careful with the sign. The local coordinate system, x3 in region 3, runs in the opposite direction to x2, so the physical slope is the same, but the mathematical expression will have an opposite sign, and this gives the condition the slope at 2 when x2 equals L minus 2a has to equal minus the slope at 3 when x3 equals a. Together with the two boundary conditions at the supports, these give us a total of 6 conditions for the unknown 6 integration constants. From this point onwards, the problem reduces to solving a system of equations, and the remaining steps are purely mathematical. We've finished with all the structural interpretation at this point. We're now going to start going through the conditions to solve the constants. We'll begin with the boundary condition at the left support. As we said, at support A, the deflection must be 0. In region 1, this corresponds to the condition y1 when x1 equals 0 equals 0. Since we know that the general deflection expression in region 1 is px1 cubed over 6 plus c11 times x1 plus c12, we will now apply that boundary condition by substituting x1 equals 0 into the expression. Both the terms involving x1 vanish, leaving only the constant term, and this gives us that c12 equals 0. Knowing that c12 equals 0, we can simplify the deflection expression for region 1 to px1 cubed over 6 plus c11 times x1. In a similar manner, we can now apply the boundary condition at the right-hand support. At support D, the deflection must be 0, and in region 3, this corresponds to the condition that y3 when x3 equals 0 equals 0. The general expression for deflection in region 3 is px3 cubed over 6 plus c31 times x3 plus c32, and applying the condition x3 equals 0 into this expression makes the two first terms vanish, leaving only the constant term. And this gives us that c32 equals 0. And once again, we can simplify the deflection expression for region 3 to px3 cubed over 6 plus c31 times x3. We now apply the continuity condition on slope at B. This connects regions 1 and 2. At point B, the physical slope of the beam must be continuous. In terms of the local coordinates, that gives the condition that the slope of region 1 when x1 equals a has to equal the slope of region 2 when x2 equals 0. We'll start off by writing the slope expression in region 1 and substituting that x1 equals a. And that results in the slope at that point being pa squared over 2 plus c11. We'll write the slope expression in region 2 using x2 equals 0. This eliminates the terms involving x2 and leaves us with the expression of c21. Now both these slopes have to be equal, and this gives us the first equation linking the constants. Pa squared over 2 plus c11, that's the slope at point B defined by region 1, equals c21. That's the slope at point B as defined by region 2. We'll now apply the continuity condition on deflection at point B. At point B, the deflection of the beam must be the same when approached from either side. So we'll begin with the deflection expression as determined by region 1, when x1 equals a. And this gives us pa cubed over 6 plus c11 times a. Next, we write the deflection expression in region 2, when x2 equals 0. This eliminates the terms involving x2 and leaves us with the expression ei(y2) when x2 equals 0 equals c22. Equating the deflections at point B gives us the second equation linking the constants. Pa cubed over 6 plus c11 times a, the deflection at B as determined by the equation from region 1, equals c22, the deflection at B as determined by the equation for region 2. We'll now move on to the continuity conditions at C, starting with the slope condition. At point C, the physical slope of the beam must be continuous. However, we need to be careful with the sign because the local coordinate system in region 3 runs in the opposite direction. In region 2, we'll take the slope condition and we will substitute point C where x2 equals L minus 2a. And that gives us the expression of P times A, all that times L minus 2a, plus c21. In region 3, the slope expression, once we substitute x3 equals a, gives us pa squared over 2 plus c31. Because the coordinate x3 is measured from the right-hand support back towards C, the mathematical slope in region 2 has the opposite sign to the physical slope. Therefore, the continuity condition, the slope of region 2 when x2 equals L minus 2a, has to equal minus the slope defined in region 3 when x3 equals a. Substituting the expressions gives us the next equation linking the constants. Pa times L minus 2a plus c21 equals minus the expression that we got for slope from region 3, which is pa squared over 2 plus c31. And the last condition is the continuity of deflection at point C. At point C, the beam is continuous, so the vertical deflection must be the same when approached from either side. In terms of the local coordinate system, that means the deflection from region 2 when x2 equals L minus 2a must equal the deflection as defined in region 3 when x3 equals a. Beginning with the expression in region 2 and substituting x2 equals L minus 2a gives us the expression pa L minus 2a squared over 2 plus c21 times L minus 2a plus c33. If we write the deflection expression in region 3, when x3 equals a, we'll arrive at pa cubed over 6 plus c31 times a. Equating the deflections at point C gives us the final equation linking the remaining constants. At this point, all boundary and continuity conditions have been stated, and the full system of equations is ready to be solved. Now, as I mentioned before, this is now purely a mathematical solution. At this stage, the first two conditions, the zero deflection at the supports, have already been applied. They gave us C12 equals 0 and C32 equals 0, which we took into account in the deflection expressions. So we're now left with four unknown constants, C11, C21, C22, and C31. From the continuity conditions at B and C, we have four equations relating to the four unknowns. Equation 1 from the continuity of slope at B, equation 2 from the continuity of deflection at B, equation 3 from the continuity of slope at C, and equation 4 from the continuity of deflection at C. At this point, all the mechanics are complete, and what remains is to solve the system of four simultaneous equations to determine the remaining integration constants. We'll now start by solving the system of equations by expressing some of the constants in terms of a single unknown. From equation 1, which came from continuity of slope at B, we can arrange directly to express C21 in terms of C11, and we get that C21 equals pa squared over 2 plus C11. Next, from equation 2, which came from continuity of deflection at B, we'll rearrange that to express C22 in terms of C11. And this gives us PA cubed over 6 plus C11 times A. We'll move on to equation 3. This came from the continuity of slope at point C, and we'll start by writing equation 3. First, we'll expand the right-hand side to remove the brackets. Then we'll rearrange to make C31 the subject. Following that, we can substitute C21 using the result that we just got on the previous slide from equation 1, and this ends up by giving us that C31 equals minus PA squared over 2 minus PA times L minus 2A minus, in brackets, PA squared over 2 plus C11. And we can simplify this further to minus PA squared minus PA times, in brackets, L minus 2A minus C11. At this point, we can stop and simplify the p terms further so the expression is cleaner before substituting into the final equation. We'll just simplify the expression that we got for C31 on the previous slide further. We'll start with the expression from the previous slide, expand the middle term, substitute it back in, combine the PA square terms, and factor out P, which will give us a cleaner expression of C31 equals PA times A minus L minus C11. Using this simplified form, we can substitute it into the final equation to determine the remaining constant. Just before we do that, let's summarise the expressions we've obtained for the remaining constants in terms of a single unknown C11. From the earlier equations, we got C21, C22, and finally C32, all expressed in terms of C11. The final step is to substitute these expressions into equation 4, which we've not used yet, and this will give one single equation with one unknown, which we'll then solve to determine C11 and then back substitute to find the remaining constants. So, returning to equation 4, which came from the continuity of deflection at point C, we'll start by writing the equation in its original form, as you can see on the top of the slide. We'll then substitute the expressions we've obtained for the constants in terms of C11. I'm just writing out, because it's quite long, the left-hand side first and then the right-hand side before equating. And you can see what they are on this slide. So you can see the full equation at the top of this slide, and now we'll simplify it to find and isolate the unknown C11. Starting from the substituted form of equation 4, we note that the term PA cubed over 6 appears on both sides, so we can cancel this term on the left and right-hand sides. We can then expand the terms involving C11 on the left and combine the terms for C11 on the left, which reduces our equation. From that point, we can collect the term C11 onto one side and the known terms on the other, and then solve for C11. So let's do that next. We'll complete the rearrangement to solve for C11. So starting from the previous line, we move the term minus C11 from the right to the left. Then we combine the terms involving C11 and rearrange the expression to isolate C11. Moving the known terms to the right-hand side gives us that C11 times L equals PA squared times A minus L minus PA times L minus 2A, all that squared, divided by 2, minus PA squared over 2 times L minus 2A. We can simplify the right-hand side, leading us to a neat result, and dividing by L, and we'll end up with C11 equals PA times A minus L over 2. At this point, we've determined the value of C11, and we can back substitute to find the remaining constants. First, we'll back substitute the value of C11 to find C21 using the expression from equation 1, and we'll obtain that C21 equals PA times 2A minus L over 2. Next, we'll find C22 using the expression from equation 2. Substituting C11, combining everything and putting everything over 6 will lead us to C22 equals PA squared, all that times 4A minus 3L over 6. At this point, we just need to repeat the process to find out C31. So from earlier, we had a simplified relationship. Substituting C11 results in C31 being PA times A minus L over 2. And we can now summarise the final values of the integration constants. From solving the system of equations and back substituting, we've obtained expressions for C11, C21, C22, and C31. Everything now has been determined, and we just need to substitute these values back into the slope and deflection expressions to obtain the final equations for rotation and deflection in each region of the beam. So, writing down the final slope equations in each region, just by substituting the constants into the expressions, we end up with a slope in region 1 being p over 2 times x1 squared plus a times a minus l. In region 2, we end up with a slope equation equaling p times a, all that times x2 plus 2a minus l over 2. Here, the slope varies linearly with x2, which is consistent with the constant bending moment in the region. And in region 3, we obtain p over 2 times x3 squared plus a times a minus l. This expression, just like the one in region 1, shows that the slope varies quadratically with position in region 3. These expressions give the complete description of the slope of the beam in all three regions. And we can now write down the final expressions for deflection in each region by substituting the constants. In region 1, we realize that the deflection is p over ei times x1 cubed over 6 plus a times a minus l over 2 times x1. This satisfies the boundary condition of zero deflection on the left-hand support and varies cubically with position, as expected in a region of linearly varying moment. In region 2, we end up with this slightly longer expression on the slide, and here we can see that the deflection varies quadratically with x2, and this is consistent with a constant bending moment between the 2 point loads. And in region 3, we have the same functional form as the deflection in region 1, again reflecting the symmetry of the beam with the coordinates measured from the right-hand support. Together, these three expressions fully describe the elastic curve of the beam. They can now be used to evaluate quantities of interest, such as slope of the supports and maximum deflection of the beam. So we were requested to evaluate the slope at the left-hand support A. This is in region 1, so we need to use the region 1 slope expression, which we found, and the local coordinate at A is x1 equals 0, so we need to substitute that into the slope expression. Dividing by EI results in the slope at A being minus PA L minus A over 2EI. The negative sign indicates that the slope at A is downwards to the right, which is consistent with the deflected shape of the beam under the applied loading. And finally, we can determine the last thing we were requested to determine, which is the maximum deflection of the beam. Because the loading and geometry is symmetric, the maximum deflection occurs at the midspan of the beam, where incidentally the slope will be 0. The midspan lies in region 2, so in terms of the local coordinates, this corresponds to x2 equals L minus 2a over 2. Therefore, to evaluate the region 2 deflection expression, we need to substitute that x2. After simplifying the result, we can find that the maximum deflection is minus p times a times, in brackets, 3l squared minus 4a squared over 24ei. This result gives the maximum vertical displacement of the beam under the two symmetric point loads and completes the solution for both slope and deflection. You can see here that the structural solution included identifying the regions, finding the bending moment for each region, then integrated that twice and had constants of integration, which we used the structural system to solve according to the boundary conditions and continuity conditions. Now that was the whole structural thing. The long part here was the maths, the solving of 4 simultaneous equations. But hopefully that was all clear. I hope you found this tutorial helpful, and I hope you join me again for some more beam deflection using the double integration method.